Vibration analysis. Procedures for accurate evaluation of machinery condition. Part 4. Special tests. Our agenda in this section will talk about special tests, includes 1. Startup or coast down data. 2. Bump tests. 3. Noise recording. 4. Synchronous time averaging or STA, and 5. Relative motion measurements or RMM. Accurate diagnosis of rotating machinery problems often requires one or more of the following tests. Number 1. Startup and coast down tests, to measure machinery vibration at all speeds during startup and coast down. Number 2. Bump tests, to measure the machine response when bumped or hit with enough energy to cause the machine to vibrate. Number 3. Sound or noise recordings, with a microphone to measure discrete frequencies heard with the ear. Number 4. Synchronous time averaging or STA, to remove non-synchronous vibration data. And number 5. Relative motion measurements or RMM, to determine how much one object is moving relative to another. Vibration analysis. Procedures for accurate evaluation of machinery condition. Special tests. Startup and coast down tests. This data is used to identify and verify imbalance, misalignment, resonance, and bent shafts. Startup and coast down data cannot be used in all cases because some machines will not coast when the power is removed. On other machines, the startup cannot be controlled. However, when a machine will coast where the startup can be controlled, these tests are valuable diagnostic tools. For best results, all startup and coast down data should be recorded because once the data is recorded, it can be processed as many times as necessary to obtain the desired results. If the data is processed live, you often have only one chance to take the data. If the equipment is not set up properly or other operator errors are made, this valuable data may be lost. An exact setup procedure cannot be established because there are several variables involved. However, the following information may be helpful. The real-time analyzer must have a peak-hold averaging capability. With this averaging mode, every time the peak amplitude changes at any frequency, the amplitude is written to the screen. This procedure provides a maximum amplitude plot of speed as the machine starts up or coasts down. The frequency range should be just high enough to contain the maximum speed. Warning: the lower the frequency range used, the longer the real-time analyzer takes to collect data for one average. When the machine is increasing or decreasing in speed much faster than the averaging is performed, a smooth amplitude plot or curve cannot be obtained. In this case, the curve will have sharp increases and decreases, and the frequency range should be increased to reduce the time required for averaging. The number of lines of resolution can also be decreased to speed up the averaging. Sometimes it is necessary to both increase the frequency range and decrease the lines of resolution. The number of averages required depends on the real-time rate of the analyzer, frequency range, lines of resolution, and amount of time the machine will coast. For example, real-time rate is 10,000 Hz, lines of resolution is 400. Frequency range is 200 Hz, time required for startup or coast down is 3 minutes. Then, time to perform one average is 1 divided by 10,000 divided by 400 equal to 0.04 second. Time to collect data for one average is 1 divided by 200 divided by 400 equal to 2 second. Total time for one average is 2 second. Then, since 3 minutes multiply by 60 second per minute equal to 180 second. Then, the number of average equal to 180 divided by 2 equal to 90 averages. A total of 90 averages are required for the above given parameters. Startup and coast down data may require over 300 averages, depending on how long it takes to start up or coast down. As showing below. Figure 35, Figure 36, and Figure 37 in the previous video, Procedures for Accurate Evaluation Part 3, contain the imbalance frequency response curves for velocity, displacement, and acceleration. The amplitude at 60 Hz is 0.3 inch per second. The equivalent displacement is 1.59 mils, and the equivalent acceleration is 0.29 Gs. These curves were generated with the vibration calculator program. These curves provide the frequency response for a pure imbalance condition and are used to compare with actual coast-down data to identify imbalance. These curves are also used to determine the increase in vibration associated with an increase in speed. The coast-down data from a machine that has pure imbalance and is operating below first critical should resemble these curves. Coast-down and startup data from a machine operating above first critical should resemble the curve in Figure 46. When power is removed, the amplitude decreases sharply by a small amount. This decrease in amplitude represents the loading factor. When the machine starts to coast, the amplitude follows the slope of an imbalance response curve. When the speed approaches the critical speed, the amplitude increases until the center frequency of the critical speed is reached. After the speed passes through the center frequency, the amplitude again decreases. The resulting bell-shaped curve is the envelope of the resonant frequency. By measuring the center frequency and the frequency at the half-power points, down 3 dB or 0.707 times peak, the amplification factor can be calculated as discussed in Chapter 1, earliest video talking about vibration analysis introduction. Coast-down and startup data from a machine with misalignment should resemble the curve in Figure 47. This data can identify misalignment between the bearing center lines in solo data, and misalignment between the coupling halves on operating machines. When the power is removed, the amplitude drops sharply by a slight amount. This drop also represents the load. The amplitude then remains relatively constant or flat for a specific decrease in speed. The length of the flat line is determined by the amount of misalignment. The flat line indicating a given amount of misalignment can cause a problem in a given machine. Once the problem occurs, reasonable increases in speed may not cause an increase in amplitude. In other words, misalignment may be speed-related until the problem occurs and not speed-related after the problem occurs. In this coast-down data, calculate the amplitude at the half-power point, 0.707 times the average peak of the shelf or flat line. For example, 0.707 times 0.55 equal to 0.39. Next, identify the frequency at the half-power point, 43 Hz in this case. Then measure the amount of misalignment between the coupling halves, 0.015 inch in this case. This data indicates that this machine could be operated at 43 Hz or 2580 RPM with 0.015 inch misalignment. Several measurements such as this could reveal realistic alignment standards. When a machine is operating above first critical and the shaft is bent, the coast-down data could be similar to the data in Figure 48. This data indicates that the bent shaft is not causing a misalignment problem. When the machine has a bent shaft and is operating above first critical, a distinctive dip should occur in the bell curve representing the critical speed. The reason the dip occurs is because the phase of the imbalance shifts 180 degrees each time the machine goes through a critical. The bend in the shaft stays at the same place, and when the imbalance shifts 180 degrees, the imbalance must be out of phase with the bend in the shaft for a very short period of time. When this occurs, the machine tries to balance itself, and the amplitude drops. Since the phase shift occurs very fast, the imbalance returns as the coast down continues. Analysis is complicated when both misalignment and a bent shaft are present. The data in Figure 49 was taken from the center bearing on a 3-bearing turbine generator set. The shelf or flat line indicating misalignment is present. The distinctive dip in the critical speed envelope indicates a bent shaft. When this occurs, the questions that often arise are, is the misalignment causing a bow in the rotor, or is the bow in the rotor causing the misalignment? In either case, the machine must be removed from service, physical measurements must be made, and the necessary repairs must be accomplished. Vibration analysis. Procedures for accurate evaluation of machinery condition. Special tests. Bump tests. Bump tests are often required to determine natural frequencies when startup and coast-down tests cannot be performed. A bump test is performed by placing a transducer on the machine or part and then hitting or bumping the unit with enough energy to excite the natural frequencies. The real-time analyzer should be set up for a dual display with both time and frequency data, as in Figure 17 and Figure 18 as mentioned earlier in the video of Procedures for Accurate Evaluation Part 1. The analyzer should trigger from the time data with a delay to display the beginning of the pulse. The data in Figure 17 and Figure 18 was recorded with a microphone while bumping a crystal glass. The glass was filled with water to obtain some damping. The dip in the time signal in Figure 18 reflects the impact when the glass is struck. The glass has three natural frequencies, and the higher frequencies are not harmonics of the lower frequencies. Also, note the frequency spectral line at 487 Hz in Figure 17 is wide-banded, and the time signal is relatively well-damped. The frequency spectral lines in Figure 18 are narrow-banded, and the time signal is relatively undamped. Bump tests are not effective on all machines or parts because of size, energy required, etc. When bump tests are performed, care must be used when placing the transducer. If the transducer is placed in the direction of the hit or bump, only the natural frequency of the transducer may be excited. Precise rules cannot be given on transducer placement for every case. As a general rule, the transducer should be placed on the part where the response is expected, and the part should be bumped in such a way as to cause the response. Trial and error of transducer placement, locations, and magnitude of bumps often yields the best results. Vibration analysis. Procedures for accurate evaluation of machinery condition. Special tests. Noise recording. A microphone and recorder cannot be used in all cases to diagnose problems in rotating machines. However, many cases arise when a microphone is the best transducer to use. Noise should be recorded to. Number 1. Prove or disprove that machine problems are causing the noise. Number 2. Identify the source of the noise. Number 3. Determine the frequency and amplitude for noise abatement projects. And number 4. Determine the correlation between sound pressure levels or SPL and vibration levels. Figure 50 contains the frequency spectrum of the noise recorded in a compressor building. The frequencies measured are vane pass frequency of the low-pressure compressor, 375 Hz, and the high-pressure compressor, 775 Hz, plus harmonics of these frequencies. The zero-to-peak value of the highest peak is about 64 decibel. The RMS value is about 88 decibel, or an overall zero-to-peak value of 1.414 multiplied by 88 equal to 124.4 decibel. At this level, pain is felt in the unprotected ear. The cause of the high noise in the room and the high vibration level on the compressor is vane pass frequency. When the problem in the compressor is fixed, the noise and vibration may be reduced to acceptable levels. Vibration analysis. Procedures for accurate evaluation of machinery condition. Special tests. Synchronous time averaging or STA. Since frequencies add, subtract, mix, and beat, and various combinations of some frequencies equal other frequencies and/or harmonics of other frequencies, accurate analysis is difficult, errors are made, and some problems are overlooked. In these situations, synchronous time averaging must be used to identify and isolate the contribution of each vibratory component. Synchronous time averaging is required for accurate diagnostics of. Number 1. Press and calendar rolls in paper machines. Number 2. Embossing/pattern and backup rolls in converting and plastics plants. Number 3. Work and backup rolls in rolling mills. Number 4. Certain gear problems. And number 5. Defect size in anti-friction bearings. The equipment required includes various transducers, a high phase or a once per revolution trigger, and a real-time analyzer capable of synchronous time averaging or STA by triggering from an external trigger or the time domain signal. Arithmetic averaging, as accomplished by most analyzers, randomly fills the memory with data, performs a fast Fourier transform or FFT, and stores the data. As soon as these functions are completed, the analyzer starts filling the memory again, performs the other functions, and presents an arithmetic average of all samples taken. This is required in all applications to provide signal enhancement because all frequencies may not be present in every average of the data. The amplitude of each frequency can vary from average to average. Synchronous time averaging synchronizes the start time for filling the memory with an external trigger or a repeatable distinctive event in the time signal. The memory is filled, and the data is stored. The next average is not started until the next trigger arrives. The memory is filled again, and the second average is combined with the first average. This process continues until the total number of required averages is completed. Since each average is started at trigger time, and the trigger or event occurs at shaft speed or during another event such as ball pass frequency of the outer race, etc., then all vibration related to the trigger/event should be in phase for every average. When the new data is compared with the stored data, all frequencies in phase with the trigger are retained and all frequencies out of phase with the trigger are subtracted out of the data. This means all frequencies occurring at event, trigger, speed or some exact multiple of event speed are retained. It also means that all frequencies that are not an exact multiple of event speed are averaged out of the data. Figure 51 contains the frequency spectrum and time signal of three frequencies: felt speed equal to 0.47 Hz, roll 1 speed equal to 6.7 Hz, and roll 2 speed equal to 7 Hz. The time signal displays the frequencies before they are mixed. Point 1 is the 0.47 Hz signal, point 2 is the 6.7 Hz signal, and point 3 is the 7 Hz signal. At the beginning of the time period, the 6.7 and 7 Hz signals are in phase. However, at the end of the time period, these two signals are out of phase. Since the time period between the 0.47 Hz signal and the other two signals is large, the lower frequency is always out of phase on either half of the cycle. Figure 52 contains the same signals after 4 averages. This averaging was performed by triggering off the roll rotating at 6.7 Hz. Note that the amplitudes of the 0.47 and 7.0 Hz signals are reduced by 50%. Figure 53 contains the same signals after 100 averages. The 0.47 and 7.0 Hz signals are still present, however, the amplitudes are now reduced by 90%. Since most frequencies will be in phase for some period of time during the averaging, it is hard to remove 100% of the non-synchronous signals. If we define the synchronous data as the signal and the non-synchronous data as noise, then the signal-to-noise ratio is improved by the square root of the number of averages, where usually abbreviated as n. Some examples of synchronous vibration are: Number 1, speed of the roll used as a trigger. Number 2, gear mesh frequency. Number 3, blade or vane pass frequency. Number 4, sideband frequencies caused by eccentricity. And number 5, frequencies generated by bars on rolls. Some examples of non-synchronous vibration are: Number 1, speeds of all rolls and shafts not used as a trigger. Number 2, noise. Number 3, bearing frequencies. Number 4, some sideband frequencies caused by looseness. And number 5, some harmonic frequencies caused by looseness. If a real-time analyzer will trigger from the time signal and the time signal contains a repeatable distinctive event, such as a defect on a bearing inner race or outer race, synchronous time averaging can be performed. For example, if a bearing has a defect on the outer race, synchronous time averaging or STA sources using the time signal for a trigger could remove most of the vibration not related to the bearing defect. The sources of the data removed could be shaft speed and harmonics, gear mesh frequency, blade/vane pass frequency, and other bearing defect frequencies. The resulting improved signal facilitates a more accurate diagnosis and description of the problem. For more examples of synchronous time average data, please refer to the last chapter of these vibration analysis video that would talk about analyzing and solving press roll and nip problems. Vibration analysis. Procedures for accurate evaluation of machinery condition. Special tests. Relative motion measurements or RMM. It is beyond the scope of this book to give an example of every case where relative motion should be measured. However, it is important to emphasize the need and general application of relative motion measurements. A relative motion measurement measures how much one part is moving relative to another part. The measurement is normally made in thousandths of an inch or mils. This is not a new measurement technique. It has been used for years with an instrument called the dial indicator. We now have electronic dial indicators called displacement transducers. These transducers can be of the contacting type or the non-contacting type. The contacting type, or linear variable differential transformer, LVDT, has been used for years in the gauging industry. The non-contacting type, or proximity probe, has been used for years in the turbo machinery industry to measure relative shaft motion in fluid film bearings. The use of these instruments in both applications has been quite successful. Portable variations of these transducers have been used for years to accurately diagnose problems in rotating machines. The major advantages of these transducers over the dial indicator are: Number 1, the output can be processed on an RTA to obtain a time signal and frequency spectrum. Number 2, they can be used while the machine is in operation, often without adversely affecting the operation. And number 3, they can be used to diagnose defects in anti-friction bearings on shafts rotating less than 1 RPM. Refer to the for example in the next chapter of this vibration analysis video talking about procedures accurate diagnosis of anti-friction bearings. Number 4, they are required to diagnose gear problems in slow-speed machinery when the gear and shaft weigh less than about 10% of the housing weight. Refer to the for example in the next chapter of this vibration analysis video talking about procedures accurate evaluation of gears. Number 5, they are required to measure the roundness of operating steel rolls. Refer to the last chapter of these vibration analysis videos, analyzing and solving press roll and nip problems for examples. Number 6, they are required to measure the amount of looseness in a bearing, the bend in a shaft, and the amount of misalignment in a coupled machine. Number 7, they are required to measure the relative motion measured between two beams or structures before bracing is attempted. The data in Figure 54 shows the relative motion measured between a turbine and the coupling. The spectral line at 35 Hz is 2 times fan speed and is caused by a problem in the fan. 3 mils at 35 Hz equals about 0.36 inch per second of velocity. The spectral line at 72.5 Hz is turbine speed. 6 mils at 72.5 Hz is about 1.4 inch per second of velocity. These vibration levels are excessive, and the data indicates a problem in the fan and misalignment between the turbine and gearbox. The data in Figure 55 shows the relative motion measured between a motor housing and the shaft. The spectral line at 7.5 Hz is motor speed and indicates imbalance. 12 mils at 7.5 Hz is equal to about 0.24 inch per second of velocity. Since more than one problem can generate the same frequency, relative motion measurements are often required to accurately identify the problem and distinguish between imbalance, looseness, bent shaft, etc. In conclusion, the technology presented in this chapter should be helpful in accurate diagnosis of machinery problems. There are many quick-fix principles and schemes available for machinery diagnostics and most, if not all, have some merit. However, people in the vibration analysis field have a responsibility to achieve as much accuracy as possible. Thank you.